All right. Hello, folks. Good to see a few of you in here already. We'll just wait a couple more minutes until 11, and then we'll get the lesson started. Welcome, folks. Start in about a minute. All right, looks like we've hit 11 a.m. So welcome everyone to the 15th day of remote learning. Today we have an appropriate joke for the weather. What kind of math do snowy owls like? Algebra. So happy Monday. Solve that like button to show your support and to get more terrible jokes. Today's lesson, we're going to be focused on trigonometric identities. Much like the work that you did in grade 11, we're just going to talk briefly about how to solve them and then practice using some of the new identities. And at the very beginning, we're going to go through the trig toolbox and fill out all of the different identities. So that's our plan for today. On Wednesday, we're also going to spend some more time on trig identities. There won't really be a lesson on Wednesday. We will have a live stream, but it'll be a chance for you to ask some questions. I'll do a couple identities at the start as examples, but mostly it'll be a chance for you to ask questions about any identities you want to ask about. So the homework for today is going to be identities 1 to 3 of 3 different groups. So there's different types of identities we're going to be working on. So I'd like you to do 1 to 3 of each of those. Wednesday's homework is going to be 4 through 8 from each of those. So if you have time between now and Wednesday, take a few moments and look over 4 through 8, and that'll help you get to questions faster on Wednesday, because our goal on Wednesday is for you to be able to answer your questions about the identities. So that is the goal. One last thing before we jump into the lesson. Linked in the Google Classroom is a survey for you to give me some feedback about how the live stream lessons are going, and whatever you'd like to see change and improve. I know it's really easy when you get that kind of survey to just say, oh, it's fine, or something like that. But please do try and think critically. If you don't tell me what I can do better, it's really hard for me to figure out. And I'm sure that under the current circumstances, there are things I can do better. There's things I can do better when I'm in the classroom, and this is certainly not as good as that. So each trig identities document from the Google Classroom. I'm going to bring the camera down here. Rotate, and there we go. Okay. All right. So we're looking at that 3.08H trig identities, and we're not going to do all of the questions here, but we're going to do a few of them. Then on Wednesday, we'll catch up a few more. And we're going to start by filling out this trig toolbox. So I had a couple questions from students since the last two lessons about whether we should fill out this toolbox, and there's many identities here you don't know. We're going to talk them through. For each of these identities, or at least the ones we haven't done yet, they are based on transformations. So they're all a transformation according to the normal transformations that we know of sine, cosine, or tan. And they're all transformations that give a different trig function. So by going into Desmos and simply playing around by subbing in, or by writing in the identity left side, you can take a look at the graph and see, is that a sine graph for most of these? We won't go through and do that for each one in Desmos, but if you want to see the proofs of them, that is all you need to do, is just look at the transformed graph on the left side and notice that it's identical to the graph on the right side, and therefore the two functions are identical. Okay, so we'll jump right in with the parity identities. So parity, oh, that needs an auto-focusing, and lamp. There we go. Okay. So we're filling in that trig toolbox in our handout. I see you got one more person just joined. So we're looking at the 3.08H trig identities handout that's posted up in the classroom, and we're just going to fill out the trig toolbox here. So the first one is sine negative x, and we mentioned this one last week, and we said, hey, this is sine is an odd function, and we know that when you apply an odd function to negative x, that you get the negative sign out front. So because sine is an odd function, this is what we get for sine negative x. Cosine, on the other hand, is an even function, which means when you do cos of negative x, you're just going to get cosine of x. Tan is an odd function. So when we do tan negative x, we can do negative tan of x. And if you want to prove this one, there's a very easy proof for it, which is to simply use the identity that tan is sine over cos, and then apply the two identities for sine and cos of negative x, and we'll get negative sine of x over cos of x, and therefore that's going to equal to tan of x. Oh, pardon me, to negative tan of x. And so that gives us our identity. Okay, so that's parity identities. Keep looking and answer them when I see them. So our second grouping here are the cofunction identities. And these are called cofunction identities, I'm guessing, because they switch which function it is. So sine pi by 2, which is the same as 90 in degrees, minus theta equals cosine of theta. So you can see we've gone from one function to something you could call its cofunction. Cosine, we get the same thing. And these two identities actually are based on the very definition of sine and cosine. So you can put these into Desmos and just test them out that way as transformations to see that they're identities. But another way to think about it is if you have a 90-degree triangle, all three angles add up to 180. So the two angles that aren't the 90-degree angle have to add up to 90, because then when you add them with the 90-degree angle, you'll get 180. And since in a 90-degree triangle, the sine of an angle is opposite over hypotenuse. So maybe I'll draw a quick 90-degree triangle here. So if I have this angle and this angle, are going to be 90 degrees together. So that means that this angle here is pi by 2, or 90 minus theta. So the claim of these cofunction identities is that the sine of this angle is the cosine of this angle. Well, that's really easy to see because the sine of this angle is adjacent. Oh, let me just check to make sure that's on screen. Yes, okay. The sine of this angle is opposite over hypotenuse, and this is the opposite. The cosine of this angle is adjacent over hypotenuse, and for that, this side would be the adjacent. So both of these functions are evaluating this side divided by the hypotenuse. So of course they're going to be equal. Exact same argument for why cos pi by 2 minus theta is equal to sine theta. For tangent, it's a tiny bit trickier. Pi by 2 minus theta. And that's just that it's going to be cotangent theta. And you can check that one in Desmos. And then cotangent pi by 2 minus theta, unsurprisingly, is just going to be tangent of theta. And I do wish that we were in a classroom where it was a little easier to show you these things and give you a chance to work them through. But unfortunately, we are limited to where we are. So quotient identities. These ones are the ones that you know from grade 11. One of the most famous, or perhaps the most famous trig identity, is the identity for tangent. And that is that tan theta equals sine theta over cos theta. And it's called a quotient because we've got a division. Nothing complicated there. Cotangent theta, well, cotangent is 1 over tangent. And if you do 1 over a fraction, you end up just flipping the fraction. So cos theta, sine theta. And there we go. So I'm just doing a quick check of the chat. I noticed there aren't really any questions. Do stop me or type your question in there if there's anything you want to know. So reciprocal identities, I hesitate to call these identities. They're more definitions. But we do use them as we're solving identities, and they are equal to each other. So in that sense, they're identities. So the first one is sine theta equals 1 over, in other words, the reciprocal. So it's always a little tricky to remember. I just try to remember their crossover. So for sine, it starts with cos. It's cosecant theta. And for cos, it does not start with cos. So it's secant theta. So cos and cosecant don't match up. The two that start the same don't match up. And so then we have those. And for tan theta, we have 1 over cotangent theta. So then we also have cosecant, secant, and cotangent. Hopefully you remember them, but also you can get them directly from these, right? If we switch sine and cosecant here, we're going to get the cosecant identity. Same thing here. If we can switch them and get secant, here we can switch them and get cotangent. So I'm not going to write those out in full, but they are exactly the opposites of these three. You just swap which function is where. All right, so now we're into related angles with cast. I'm just going to check and make sure I can still be seen here. Yep. Related angles with cast. All right. So cast is a mnemonic, a memory tool. Stands for cosine all sine tangent. And the idea is that if we have an xy plane and our angle starts on the positive x-axis and it goes to some terminal arm like that. So let's say this is our angle. then we want to know, is it going to be positive or negative when we take cosine, sine, or tangent? And the cast rule says that in this quadrant, cosine is positive. In this quadrant, all are positive. In this quadrant, sine is positive. And in this quadrant, tangent is positive. And you can memorize that, and perhaps you already have. I personally prefer to think of it as cosine is x, sine is y, and tan is y over x, because it's sine over cos. So here, x is positive, y is positive, and y over x obviously also positive. So cosine, sine, and tan are going to be positive. In this quadrant, y is still positive. We're above the x-axis, but now the x values are negative. So cosine is going to be negative. Sine is going to be positive. Positive divided by negative is overall negative. So tan is going to be negative here as well, leaving just sine as the positive one. And then if we move here, in this quadrant, the x-axis is negative, the y-axis is negative. And so cos is negative, sine is negative. But negative divided by negative is positive, so tan is the lone positive one here. And then in the last quadrant, x is positive again, y is negative. So cosine is positive, sine is negative, negative over positive is negative. So tan will also be negative, leaving cosine as the only positive one there. So you can remember cast, but if you know that cosine is x coordinate divided by the radius, sine is the y coordinate divided by the radius, and tan is the y coordinate divided by the x coordinate, then it's very easy to figure out which one is going to be the positive ratio. Okay, so again, just doing a quick sneak back and forth here to make sure that I haven't missed any questions and that I'm still in your field of view. Okay. So related angles with cast, we can keep this in mind. Pi minus theta, as you can see in the drawing there, it is in this second angle, or this second quadrant. So if we want to look at sine of pi minus theta, that's just going to be sine theta. We're going to be in this quadrant, so the y values are the same. Sine only depends on the y value, so we're in good shape there. For cosine, we are again into this quadrant, so it's going to be negative. And for tan in that quadrant, we're also going to get negative result. You can see from the picture that now we're into this third quadrant here, which is our tangent quadrant. Just erase that other line. So now we're talking about an angle that goes like this, stops here. Well, that's going to give the same values for sine, cosine, and tan, except that all of them except tan will be negative. So if we do sine pi plus theta, we get negative sine theta. Cosine of pi plus theta, we get negative cos theta. And tan of pi plus theta, well, now this is the quadrant where tan is positive. And then our final one is 2 pi, which is a full circle, minus theta. So we're moving back by theta. So now instead of being in first quadrant, we're all the way around in the last quadrant. And so cosine is going to be the only positive one. 2 pi minus theta. Oh, sorry, not cosine. Sine. And it's negative theta. Cosine is our positive one. and tan is still negative here. Negative tan theta. All right, so those are the related angle identities. You heard me talk about them as based on transformations. And I just want to give you a quick example of what I mean by that, because it shows a whole different way to prove these. So 2 pi is the period of sine and cosine, and it's twice the period of tan. So if we're adding 2 pi to an angle, we're just moving the whole wave by one wave. So that's not going to change it, right? If you add 2 pi to any angle and then take the trig ratio, you're going to get the same answer as if you didn't add 2 pi. And that's because you've moved the entire wave exactly one wavelength over, and so it's on top of itself again. So adding 2 pi doesn't change anything, which means this is basically the same as sine negative pi, or negative theta, pardon me, which we already knew was negative sine theta. So there you can kind of see the transformations thinking making these easier. Okay, compound angle identities, double angle identities, those ones we've already learned in the last few lessons. I'm going to let you fill them in. If you're having trouble filling them in, just take a look back at your notes. But they're ones that you want to learn. You'll notice there's a few different possibilities for cosine 2x. And so we can take a look at what those are for cosine. So I'll give you a little fill in there on those ones. So cosine of 2x, the one we know is cos squared x minus sine squared x. And then from there, it's pretty easy to get the rest of them. The first thing that we do is we know that, well, why don't I do this in a bit of a better organized manner here. Let's finish the trig identities because we're going to use those, or sorry, the Pythagorean identities, because we're going to use those to get the other cosine identities. So we'll do Pythagorean. So the first one is cos squared x plus sine squared x equals 1. And that is simply, it's called the Pythagorean identity because if we look at an angle on the xy plane and we make this right angle triangle from the end of that angle, this side is the x coordinate of this point. This side length is the y coordinate of that point. This squared plus this squared is equal to hypotenuse squared. But if we have a unit circle, which is what we've been using, then the hypotenuse is 1, so square it, it's still 1. And x and y are just cos theta, and I should guess use thetas here, so as not to be confusing, theta and theta. So this length is just the cosine, because adjacent over hypotenuse when hypotenuse is 1 is just adjacent. Opposite over hypotenuse, well, if the hypotenuse is 1, that's just opposite. So sine is y. So x squared, that's cosine, y squared, that's sine squared, and hypotenuse squared, that's 1. So this is literally the Pythagorean theorem. And then from here, we have a few rearrangements we can do. So the first thing we can do is we can say, okay, well, cos squared theta is equal to 1 minus sine squared theta. We just subtract sine squared from both sides. Or we could have just subtracted cos squared from both sides, get 1 minus cos squared theta. Both of these come up very frequently, probably more than the original one when you're doing trig identities. So it's really good to get to know them. Just take a quick check of the chat. Okay, no question so far. And then we do have a couple other Pythagorean identities. So if we took the original and we divide both sides, every term, by cos theta, or cos squared theta, rather, then we'll get 1 plus, well, sine over cos is tan. So sine squared over cos squared is tan squared. And 1 over cos is secant. So 1 over cos squared is secant squared. So we get this new identity here that is a Pythagorean identity, and we got it from the original, just dividing everything by cos squared. If we take the original, we divide everything by sine squared instead of cos squared. Then we get cos squared over sine squared, which is cotangent squared, theta. Sine squared over sine squared, which is 1. And 1 divided by sine squared, which is cosecant squared. And then oftentimes people will do this, they'll rearrange this in a lot of different ways, move the 1 over, move the cotangent over, etc. But there is the basic Pythagorean identity. Okay, so now we'll go to the double angle formulas where there's the multiple cosines. So we have this one as our first one. Our second one is to say, hey, cos squared x. Well, we have a Pythagorean identity that tells us cos squared is 1 minus sine squared. So cos 2x, we can go 1 minus sine squared in place of cos x and keep minus sine squared. And then obviously we're going to want to collect our like terms here. So we'll go 1 minus 2 sine squared x. So that's pretty useful. And then we also have the ability to replace sine squared with 1 minus cos squared. So we could do cos 2x equals cos squared x minus 1 minus cos squared x. You'll notice I put it all in brackets so that I make sure to distribute the negative sign. And cos squared x minus negative cos squared x, that's 2 cos squared x. Subtract 1. So those are our 3 cosine double angle formulas. We did this one last time around. It's helpful to know these other ones as well. Okay, so we've gone through the toolbox. What questions do you have from that before we dive in and do a couple of identities? Give you about 20 seconds. If you don't have any questions, if you can just type a 1 in the chat, let me know you're ready to move on. Thanks, Caitlin. Thank you, Daniela. Thanks, Ramisa. All right. So keeping that toolbox that we just filled out around so that we can use it, I'd like to look again at our handout. No. Sorry, I think we may be having some focusing issues. There we go. All right. So in the handout, trigonometric identities, we're looking below the toolbox here. Trigonometric identity is an equation that is true for blank. Blank in this case is all angles. So no matter what angle you put into a trig identity, it's always going to be equal. And then we have the question, is sine x plus sine 2x equals sine 3x an identity? Well, let's pick an angle like 90 degrees. Sine of 90 degrees is 1. Sine of 2 times 90, or 180, is 0. So 1 plus 0 is 1. The left side is 1. Sine 3 times 90, well, that's 270. And that's negative 1. Is it true 1 equals negative 1? No. So this is not an identity. There is a value of x, at least 1, where this is true, I think. And we could solve to find that value of x, but because it's not true for all angles, it's not an identity. Okay, we're going to skip the little fill in the blanks at the bottom, and we're going to try the first question on the next page. So it's giving us sine 2x over 1 plus cos 2x equals tan x. So I'm going to walk you through my thinking on these because trig identities is really about how do you think about the problem. There's no sort of follow these steps and you'll get the right answer process for them. It's really about thinking them through. So when I look at this, I think a few things. I think, okay, we've got double angles here, so I can use the double angle formula, and that may help me out. I see that there's a 1 here. Usually if you see a 1, it's telling you that there's a Pythagorean identity somewhere in there. If you look back at our page of our trig toolbox, you'll see that the only place you see 1 plus or minus something is in the Pythagorean identities. So anytime you have a 1 added or subtracted with some other things, it's a hint that there's a Pythagorean identity going on. And finally, I see that I've got tan x on the right-hand side, and I know that's sine x over cosine x, and I have a quotient on the left side, so that suggests to me that that might be helpful. So there's probably a whole bunch of ways to do this, but I'm just going to dive in and try the double angles first, because I know as long as I have 2x over here and just plain old x over here, I'm not going to get them equal. So let's get rid of those double angles. So we get 2 sine x cosine x is our identity for sine 2x. For cosine, we have x minus sine squared x. And we can use that one, but I have this 1 here that I probably want to get rid of. So the one that I would rather use in this case is the one that is 2 cos squared x minus 1. Okay. So this would be the most efficient way to do it. I'm actually not going to do it this way because I want to show you that you can still easily get to the correct answer without knowing that, but it does add an extra step. So let's say we just use our usual one, which is cos squared x minus sine squared x. Okay. So at this point, I'm looking at this, I'm going, all right, this is my left side, and I want to make the 2 go away and the cosine go away from the top and get cosine in the bottom. Well, if I want cosine in the bottom, this sine and this 1 need to go away. And so I look, I've got 1, I've got minus sine squared x, and I look over at my trig toolbox and I go, oh, 1 minus sine squared x, that is the Pythagorean identity for cos squared x. So cos squared x plus so this is a little note to myself, cos squared x plus 1 minus sine squared x, that's going to equal to cos squared x plus cos squared x. And so that's going to be good news. So I'm going to use that here. I have 2 sine x cos x all over 2 cos squared x. And now you can see that we're in very good shape. 2 divided by 2 is 1. Cosine divided by one of these 2 cosines is 1. And we end up with sine x over cos x. And that is equal to tan x. And therefore, left side equals right side. And it is an identity. All right. Any questions about that so far? We'll see if we can refocus that. There we go. So if you're feeling comfortable and you don't have any questions, just put a 1 in the chat, please. Thanks, Caitlin. Rumaisa asks, is it better for us to put tan in terms of sine, cos, or should we leave it as tan? That's a very good question, Rumaisa. There is a tiny little bit of controversy in the math teaching world about that question. Some math teachers say you should only work with one side of an equation, of an identity, pardon me. You should never work both sides of the identity simultaneously. Other math teachers say go ahead and work both sides. The key thing, though, and what all the math teachers agree on, is you should never work the two sides together. Okay. Yes, Danielle, I'll come to that in a second. So you don't ever want to treat this like an equation and just do the same thing to both sides. And the reason for that is that if you do that, you're kind of assuming that they're equal to start. So it's bad form, and there are a few problems that can arise if you do that. So in my opinion, you are welcome to work on the left side in one place, work on the right side in another place, and if you can get them to the same thing, then you know by just going down the left side and then back up the right side step by step, you will find the identity. So Rumaisa, my answer would be that you are welcome to have a little bit of right side equals sine x over cosine x. That is totally reasonable way to work. The one thing I would say for those of you who prefer to just work with a single side is you should always be looking at the other side and thinking in your head, okay, what are some things I can get out of that? So here, obviously, it's a lot easier if we know that tan x is going to give us sine x over cos x, because when we get to this part, we're like, hey, I want cos x's on the bottom. So I need to get rid of the sine and the 1, and that's the key insight that shortened this up considerably. So hopefully that answers your question, Rumaisa. Daniela, can I show the way if we were to put 2 cos squared x minus 1 in the bottom instead? Yes. So, or left side equals, again, sine 2x will work out the same, but in the bottom we will get 1 plus 2 cos squared x minus 1, and then you can see from here 1 minus 1, that adds to 0, and we're left with 2 cos squared x just like we were here. And so now we can go 2 divided by 2, cos x divided by cos squared x, and then we're immediately into, okay, we have sine x over cos x, that's tan x, and we are done QED. So hopefully that answers your question, Daniela. And as you can see, it is quite a bit shorter doing it that way, but some people might find it harder to remember this identity for cosine. And so that will make this method a little harder, but it doesn't matter which one you do, you get a proof either way. Okay, gonna move on now to question number 2. And I really like this question. It's asking us tan 2x minus 2 tan 2x sine squared x equals sine 2x. Can we prove this identity? Let me just check. So I'm almost off the screen here. There we go. Rumaisa, what does the square mean? Good question. So the square is, in my opinion, terrible notation. Cos squared x, and it's the same for all the others, just means cos x, all in brackets, squared. So that's all. Oh, wait, sorry, that's not the square you're asking about. You're asking about this square. This square means end of proof. So hopefully I've figured out which is the square you're actually asking about. This is just a symbol mathematicians use to show that they've ended a proof. So if you read mathematics papers published in journals or in books, they'll often have to prove several different things before they get to the main point. And so they just use this square here to show that they've ended a particular proof and now they're moving on to the next one, or they're moving back to the main one that they're going to use this to support. Okay. So let's look at this one here. Tan 2x minus 2 tan 2x sine squared x equals sine 2x. So as always, the crucial things for making your life easier are to stop and think about what you see before you dive in. So what do I see here? Well, I notice there's double angles. So we have tan 2x, sine 2x. Here, of course, it's not all double angles. So I might not be able to just do double angles. I might have to convert. But mostly it's double angles, and I've got double angles on both sides. So I might just add that to what I'm noticing here. The double angles are on both sides. Why is that important? It's important because it tells me I might not need to get away from the double angles. I might be able to just do the whole thing using double angles and never have the compound or double angle formulas. I might be able to just leave 2x in all the way through. What else am I seeing here? Well, I'm seeing a sine squared x, so there's some Pythagorean stuff going on. And slash, that might be something from a cos double angle. Because if you notice, all of the formulas for cosine 2x have squares in them, right? We had, let me show you here. So cos 2x is cos squared x minus sine squared x. Cos 2x is 1 minus 2 sine squared x. And cos 2x is 2 cos squared x minus 1. So we have a few different options. I'm going to zoom this in a bit. I feel like it's not really dark enough. There we go. So anytime I'm seeing squared stuff, that tells me it's either Pythagorean or it's the cosine double angle formula. And then the last thing that I notice here is, hey, there's a tan 2x in both terms on the left-hand side. So there's common factor tan 2x. And you can see here that it's really important to stop and look before you begin. Because if I hadn't stopped, the first thing I would have been seen is, oh, 2x, 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 okay, double angles, get working in the double angle formulas. The double angle formula for tan especially is pretty messy. If I do that substitution in here, I'm going to end up with massive algebra on both sides of this identity. Sometimes when you're doing identities, you have to have massive algebra. Okay, we'll deal with it. But if you don't have to, it's something you want to avoid. And in this case, I think we can completely avoid that massive algebra. So instead of jumping in and doing double angle to start, I'm going to go, okay, let me get this tan 2x common factored and see what that looks like. So tan 2x times, well, this was just tan 2x, so that's just a 1. Here we had negative 2. We took out the tan 2x, so we have sine squared x left. And we have that equals sine 2x. Okay, well, this is really good news because 1 minus 2 sine squared x is exactly our cosine double angle formula. So if you remember, we did this one earlier. Cosine 2x equals 1 minus, there we go, minus 2 sine squared x. So if we have 1 minus 2 sine squared x, well, that's just cosine 2x. And so now we have everything in terms of 2x. There's no reason to use double angle formulas. This is great news. It's going to shorten things, and it's going to make the algebra much, much easier. Okay, well, I need to get sine 2x, and I'm doing exactly what I told you not to do. So I should fix that and follow my own advice, which is I'm writing both sides. I haven't been working both sides, but I am writing them. I should separate them out and not do that. So left side equals, and then right side equals sine 2x, and we will keep them separate. Okay. So now I know I want sine 2x. Well, tan 2x, that's going to be sine 2x over cosine 2x. So that's a nice easy way to get sine 2x, and then times cos 2x. And now I see that these two cancel out, and the left side is indeed sine 2x. Therefore, left side equals right side. End of proof. Okay. Oh, and I've gone off the page here. So sine 2x over cos 2x times cos 2x, they cancel. Sine 2x is all that's left, and I know it's a true identity. And so if you want a challenge, you can try doing this one by doing all the double angle formulas, putting them in for tan here, and for sine here, and then digging through it. It's by no means impossible, but you'll see that it's quite a bit longer and much more complicated, and therefore much greater chance of making a mistake than this method here. So always kind of list out, what do you see that might give you an idea? Do you see a common factor? Do you see double angles? Do you see squareds that tell you that it's probably Pythagorean or cosine double angle? Do you see 1 plus or 1 minus something that tells you, again, Pythagorean or cosine double angle? All right. So I'll give you a moment to ask questions. Again, just type a 1 in the chat if you're ready to move on and all of that makes sense to you. Okay, thank you, Daniela or Minister Caitlin. We're going to do just one more. And so if you scroll down to the third page, it says more sophisticated proofs will involve trinomial factoring. And then it has a difference of squares reminder. So we're just going to do a quick difference of squares reminder and then try out the proof on the right-hand side. We'll be using quite a bit of our algebra tools this year when we're doing trig identities. And so it's good to remember them. So a squared minus b squared, well, you probably remember that's a plus b times a minus b. And this is true no matter what values of a and b are. And in particular, if a and b are sines or cosines or tangents, etc., this is still going to be true. So the identity we're trying to prove is sine squared x over 1 minus cosine x equals 1 plus cosine x. So we're going to start here and go, okay, I'm looking at both sides. I'm trying to see what's going on. And I see it sine squared x. The square tells me maybe Pythagorean or cosine double angle. But I look and there's no double angles anywhere. So that means it's probably Pythagorean, and I don't want to go into double angles if I don't have to. I also have on the bottom of this quotient a 1, which again is being subtracted, or the cosine is being subtracted from 1. So that again suggests to me that there could be Pythagorean going on. And here again I see 1 plus, which again suggests Pythagorean theorem. So I'm like, okay, this probably has Pythagorean. I take the trig toolbox, I look through, I'm like, what are my Pythagorean identities? Well, I have a Pythagorean identity that says sine squared x is 1 minus cos squared x. So I'm going to apply that one. So left side equals sine squared x, that's 1 minus cosine squared x. And I'll leave the denominator the same. Oh, blurry. Oh, and we're still blurry. There we go. Okay. So 1 minus cos squared x over 1 minus cos x. And our right side is still just going to be 1 plus cosine x. This is where the difference of squares comes in. 1 is a perfect square. Its root is just 1. Cosine squared x, obviously a square. So we can do this top as a factorization of this difference of squares. And we will get 1 plus cos x times 1 minus cos x. And from there you see that it very quickly resolves itself. 1 minus cosine x over 1 minus cosine x. That divides out to 1, and we're left with 1 plus cosine x, and that is the right side. And therefore, left side equals right side. We are done with the proof. So, there we go. Okay. So those are the ones I wanted to show you. At the bottom of the handout, the very last page, there's a whole bunch of trig identities. If you wonder, why do we spend time on trig identities? Like, they're fun puzzles, but are they really useful in mathematics? The answer is yes. In calculus, when we're trying to find rates of change, we often end up with quite complicated functions. And if those functions start with 1 or 2 trig ratios in them, when you go to find the rate of change, you can often get something which is a huge algebraic mess of trig functions. And by knowing your identities, you can often simplify that big mess down to something that is much easier to work with. So in calculus, these trig identities will actually save us a lot of time, and in some cases even make it possible to solve a problem that we wouldn't have been able to solve without them. So that's it for today. Thank you to the Waterloo Region District School Board for sponsoring this video. Just type me a 1 in the chat if you don't have any questions, and we'll end the stream. And if you do have questions, put them in the chat. I'm happy to take them. Great. Thank you, Daniela. Yes, Caitlin. Good question, Caitlin. The work to do is all from the last page. So there's 3 groupings, and they're all numbered independently on that last page. I'd like you to do 1 to 3, 1, 2, and 3 of each of those groupings. So 9 questions in total, all from the last page. Okay, and give me a 1 if that makes sense, Caitlin. Rumaisa, thank you for letting me know that you don't have any questions. Great. Thank you, Caitlin. All right, folks, that's the stream. See you on Wednesday.